So this is a video about some ticks and trips. That's excellent. Tricks and tips for how to solve problems about the center of mass. So if we had a sheet of plywood and I don't know if you know this, but a sheet of plywood is 4 feet by 8 feet, so 4 units by 8 units. And if we ask, hey, where's the center of mass for this sheet of plywood? Now the plywood is very thin in the direction that's coming in and out of the page, so it mainly is a two-dimensional object. Um, you would initially just say, hey, look, this symmetry line here cuts it in half. This symmetry line here cuts it in half. We're going to assume that plywood is made of a very uniform material. It's the same density everywhere. And even if we took our origin of our coordinate system 0, 0 to be down here, we would say that, hey, the center of mass is going to be at the center of the object, and that's got a coordinates of 2 in the x direction and 4 in the y direction. No big deal. We use symmetry. We figured out the coordinates of the center of mass. But what if it was a piece of plywood that Harmon had already carved a chunk out of? So now this is 2 feet, this is 2 feet, this is 2 feet, and this is 6 feet. That makes this 4 and this 8. So now this is a piece of plywood that I've carved into pieces. Not even a very good drawing of it, okay? How would you find um, the center of mass of this goofy looking thing? Well, you could use the experimental technique of drilling some holes and hanging it and marking lines to see where the center of mass is. But you could also imagine cutting this thing into pieces. Like, what if we cut it into 2 pieces by cutting right across here? Okay, now we have 2 pieces, each of which is symmetrical, and we can determine where its center of mass is. Now, this piece here, the big one, is 6 feet this way, and what is it? It's 4 feet across, so its center of mass is going to be right here. Again, using the same origin at the lower left corner. I don't know if that's the best choice of origin, but let's figure out where it would be. Well, the center of mass on this piece is going to be at an x of 2. And a y, instead of a 4, because this is only 6 feet, it's going to be at 3. Now, the second piece is up here, and it is symmetrical, 2 by 2 square, and so its center of mass would be there. Okay, now where is that? Okay, so we need to go up 6 feet, and then one more, so the top part is going to have its x-coordinate be 7, and then its y-coordinate is going to be 1 unit away. I'm sorry, I got those backwards. It's going to be 1, 7. There we go. Now we got to figure out how much mass each of these has. So if an original sheet of plywood had a mass of, oh, I don't know, 1, I don't know. How about this? How about we, instead of talking about mass, we talk about square footage, because whatever the square footage is. So this piece, the bottom piece, is a 6 by 4 piece. 6 times 4 is 24, so we'll assign it a mass of 24. And then this piece up here is 2 by 2, so it has a mass of 4. So now we have to find the x and y coordinates of the center of mass using an object that has 2 discrete chunks. And yes, each of those chunks is a larger object, but we've reduced the larger object down to a single point using the symmetry idea in center of mass. So in the x-coordinate, we have a piece that weighs 24 and is located at an x-coordinate of 2, and we have a piece that weighs 4, or has a mass of 4, and it is located at a position of 1, and the total mass of this object is 28, which is 24 plus 4. And so here we go, syntax error. Okay, whoa, that got ugly quick. 24 times 2 plus 4 equals 52 divided by 28 equals, this is going to be 1.85, actually 1.86 feet. And then the y position of the center of mass is going to be an object that has a mass of 24, but is located at a y of 3, plus something has a mass of 4 located at a y of 7, and that, of course, will also be divided by 28. I'm not sure I left myself enough room for this, but let's give it a try. 24 times 3 plus, parentheses, 4 times 7 is 100. Oh, that's interesting. Divided by 28 is 3.57. 3.57. Okay, so the overall center of mass of this object is going to be at an x of 1.6, that's nearly 2, and a y of 3.57. So the overall center of mass of this object is right about here. Now, why is it so close to this? Because this piece is so much larger than this piece, right? There's just a little notch cut out at the top. So that's how to take a complicated compound object and split it imaginarily into two pieces or more, and treat each of those pieces as if it's concentrated at one point. By the by, we could have made the imaginary cut this way too, and we would have gotten the same answer. I'll leave it to you to prove that. Now, there is another trick, and that is to say, what if, here, let me get my, what if Harmon has been just a complete idiot and has the taken the piece of plywood, 4x8 sheet of plywood, and has cut a 2x2 square out of it. Oh, hold on. Let's make this even more complicated. Has cut a 2x2 square out of it in a non-central location. Okay, so if this is 2x2, then let's just say that that's 1 foot down, and then that would makes the, let's see, 1 foot down, then two more, so this is 3 feet down on our way to 8, and this is 1 foot, and then 2 feet in here, and then 1 foot on that makes 4. Okay, cool. So you would have to locate where this is. How do you handle a void, a hole? How to handle a hole? Well, treat the hole as if it has negative mass. In other words, if you have a piece of plywood with a hole cut in it, and I know you can't read these little things, the pen is turning into a paintbrush. But what you do is you say, okay, this is a compound object, really hard to think about, but let's think of it as a sheet of plywood that has no hole, whose center of mass would be at a location. What did we say? It was going to be 2, 4. Okay, and then a hole whose center of mass is in its center. And this hole has negative mass. Now, we can locate where this thing is because it has x coordinate of 2 right in the center line, so 2, and a y coordinate up here that's 1, 2 down, so 6. So we would have two pieces, a piece that is the same as the whole sheet of plywood, and a whole sheet of plywood has a mass of let's see, an area of 4 times 8, which is more than 32. 48? No, it can't be 48. 4 times 8, 32. Yeah. Okay, so 32. And then this one has a mass of negative 4 because it's a hole of size 2 by 2. So that's how you would treat this. Do the same kind of calculation you did up here. Just treat the hole as if it's a piece with negative mass and combine that with a imaginary sheet of plywood that doesn't have the hole in it. There's a thing in your book about how to do this. Okay, that's one tip and trick. Tip and trick. Trick and tip. I'm going to have to learn how to say that. The second thing I wanted to show you is this density deal. So I told you that if you had to do this as an integral, you would have 1 over the total mass, and you'd have an integral of all your x positions, and you'd integrate over the mass. But you needed to swap out variables. So you would say that the density of the object is the whole mass of the object divided by the volume of the object. By the way, this doesn't have to be volume. It could be mass divided by area if you're dealing with a two-dimensional object, or even mass divided by length if you're dealing with a one-dimensional object like a rope or a board or something like that, okay? And then that also means that the density is a small incremental amount of mass divided by a small incremental amount of volume, or small incremental amount divided by a small incremental amount of area, or small incremental amount of mass divided by a small incremental amount of length. This idea means that we can do a substitution, that dm can be replaced by the density times d volume or area or length or whatever you got. So if you do that, then you've got density over mass, integral of x d vol. By the way, density over mass, and density is mass divided by volume, so we're dividing out the mass. So really, this is just 1 over the volume. Okay. Now, in practice, let's do something that's one-dimensional and show you how this works. In practice, let's just say that we had a 1 meter long stick that weighed 1 kilogram. and we wanted to find the x position of center mass using this kind of integral. Well, in this case, instead of using a volume, we're going to use length because this is a one-dimensional object. So we would have 1 over the total length, L, integral of the position, dl, or dx, I guess you could say, because it is, we're choosing 0 here, and we're going to go along the x-axis. And our limits are 0 to L. So let me fix this up. That's going to be 1 over the total length of the object, integral from 0 to the total length of the object of x dx. Okay, well, that's an integral that I can get behind here. This is a simple integral. We integrate once, so we're going to have x squared over 2. There's a 1 over L out front, and we have to evaluate that from 0 to L. So that means, let's see, putting in L here, we have L squared over L2, so we have L over 2, and then we would subtract away, putting in 0 in there, which is 0. So it would give you an answer of L over 2, or in this, for this practical case, a length of 1 divided by 2, that would be 0.5 meters. Hey, isn't that awesome? It is. It's right in the middle. That's what we said. It was going to be right in the middle. So this system works. You'll have to wrap your brain around this change of variables and if you haven't done this in calculus class, don't worry. We're not going to do too many of these in the homework until later on. All right, that's enough for now.